Hi, this is Dr. Lesher. I hope you're having a good snow day. We're going to do a quick lesson about one of the colligative properties. You already did a lab that had to do with colligative properties when Mr. Besh was showing you the magic sand and salting out. And we'll talk about how that relates in class, but today this lesson will focus just on Raoult's law. So colligative properties are properties that depend on the amount of dissolved particles. And those could be molecules or ions or even colloids. And it doesn't really depend on the chemical nature of those solute particles, just on how many are there. So there's a number of colligative properties. We're just going to focus on vapor pressure lowering in this video. So Raoult's law says that if you have a solution with a liquid solvent and a non-volatile solute, something like salt, then the vapor pressure given off by that solvent is going to be lowered. And it's proportional to the concentration of the solvent, or you could think of that as how many particles of solute there are. So there's a formula for it, and P1 indicates the vapor pressure of the solution. P1 with a 0 superscript represents the solvent completely by itself, so the pure solvent. And then X is the mole fraction. So basically, we're just multiplying the vapor pressure of the solvent in its pure phase by the mole fraction, because that represents sort of how much is actually there. Let's think about it visually. So if we have a pure solvent, it gives off some amount of vapor pressure. If we have some solute there, represented by the red circles, then those solute particles are blocking the solvent from entering the vapor phase. They're covering some amount of the surface area of the liquid, and that prevents complete vaporization, or at least vaporization to the extent as would be observed with the pure phase. So we get lower vapor pressure with a solution. So let's do a little bit of practice. This is a pretty typical problem for applying Raoult's law. The vapor pressure of a compound called hexanone is 12 millimeters of mercury. Vapor pressure is temperature dependent, so this is at 20 degrees Celsius. Now the question is, what would the pressure of the solution be if we have 25 grams of benzoic acid dissolved in 125 grams of the hexanone? And we're assuming that the benzoic acid is non-volatile, meaning it doesn't give off its own vapors. It doesn't evaporate readily. So we're going to apply this formula for Raoult's law, where we just need to multiply that vapor pressure, the 12 millimeters of mercury, by the mole fraction of the hexanone. So that means we need to calculate the number of moles of both compounds. So for the hexanone, we've got 125 grams. Its molar mass is 100.16, so that gives us 1.248 moles. And the benzoic acid, same process, divide by molar mass, and we have about 0.2 moles. So the total number of moles is 1.45, and if you recall, the mole fraction is just how much of the compound that you're interested in this case the hexanone, is there relative to the total number of moles. So the mole fraction is just the 1.248 moles of hexanone divided by the total, and we get a fraction, 0.859. You could also say that 85.9% of the molecules in the mixture are hexanone, but mole fraction is usually kept as a decimal value. So the vapor pressure of the mixture is just that mole fraction times 12, which gives us 10.3 millimeters of mercury. So by adding in that non-volatile solute, we reduce the vapor pressure of the hexanone. So we can also apply Raoult's law when we've got two liquids that are both volatile mixed together in solution. And so let's imagine we have liquid A and liquid B, yellow and purple. And liquid A gives off a vapor pressure that's equal to P sub A naught, so that's the little 0. And liquid B gives off a lower vapor pressure that's symbolized in this cartoon by there being fewer molecules in that gaseous phase for the purple. So Raoult's law says that if we mix together these two liquids and they're both volatile, the total vapor pressure is just going to be the sum of their individual contributions. And their individual contributions are, for liquid A, the mole fraction of A times its original vapor pressure, and for B, the mole fraction of B times its original vapor pressure. So quantitatively, we can define the total vapor pressures that as those two contributions, and we can combine the expressions for those two contributions into a formula for the total vapor pressure. And let's think about why this law is the way it is too. If we mix together these two liquids in some proportion, this is showing a higher proportion of the yellow A liquid in this little cartoon. We're just going to get kind of a representative amount of vapor that's generated from this mixture. So compound A evaporates more readily. It has the higher original vapor pressure, and there's more of it. So there's a pretty good deal of vapor A in the gaseous phase. There's less of liquid B, and it has a lower vapor pressure, so it's only giving off, what's symbolized here is just these two little molecules, but a lower amount of vapor pressure. So let's work through an example with using this formula. So let's say we have a solution of two organic compounds, benzene and toluene, and we've got 155 grams of benzene, 265 grams of toluene. And at a certain temperature, a certain constant temperature, toluene has a vapor pressure of 300 millimeters of mercury, and benzene is at 750. So if we apply that formula, that we're going to multiply the mole fractions times the individual vapor pressures and sum them, it's clear that we first need to find those mole fractions. So we'll first convert the masses of both compounds into moles. We'll sum those molar amounts. The mole fraction is simply the number of moles of each divided by the total molar amount. So for the benzene, we end up with about 0.4, and for the toluene, we end up with about 0.6. So the total vapor pressure is just the mole fractions times those individual vapor pressures, and we end up with about 306 contributed by the benzene and 177 contributed by the toluene, to give an overall vapor pressure of 483.7 millimeters of mercury. Now, one thing is that Raoult's law doesn't always perfectly apply in reality. It does when we have what's called an ideal solution, and I'll talk about what that means shortly. This little chart here kind of gives the expected vapor pressure of a mixture no matter what the proportions. And so let me explain this graph a little bit. On the x-axis is the mole fraction of benzene, so ranging from no benzene, mole fraction of 0, to all benzene, a mole fraction of 1. And then the expected vapor pressure on the y-axis. So we can see that benzene, if it's completely 100% benzene, we have a vapor pressure close to what we were given as benzene's typical vapor pressure at this temperature, which is about 750. So that's at x equals 1. At x equals 0, then we've got all toluene, and so we have a vapor pressure equal to toluene's vapor pressure, about 300 millimeters of mercury. And so as the proportion changes from no benzene to increasing amounts of benzene, we get a greater and greater vapor pressure because benzene has the greater vapor pressure between those two compounds. And the dashed lines are just representing the contributions from benzene, so when we have none, there's 0, but then that line quickly slopes up to the total amount if we have all benzene, and same with the toluene. If we compare our previous calculation to this graph, we were expecting that with a mole fraction of about 0.4 for the benzene, we would end up with about 484 millimeters of mercury. So let's see if that works out. 0.4 for the mole fraction of benzene gives us a vertical line here, and so the total expected vapor pressure does fall right about where we would expect it to. So really, using mole fractions and multiplying them by the vapor pressures is actually just kind of a weighted average type calculation to give us the weighted average between the two vapor pressures. Now, back to ideal solutions. Ideal solutions means that the intermolecular forces between the two compounds, between benzene and toluene, are similar to what would be expected among molecules of just benzene and among molecules of just toluene. And so there's not excess attraction or different levels of attraction between the two compounds. So scenario 1 is kind of the ideal scenario. But let's think about some non-ideal scenarios. So scenario one is that we might see vapor pressures less than what's predicted by a Raoult's law calculation. And so what this would look like is, we've got compounds A and B, and as the mole fraction of A increases from 0 to 1, we're seeing, we would expect the vapor pressure calculation to be kind of predictable, but we'd actually see lower vapor pressures than predicted. So what does this mean? Let's think about the forces involved. If we're seeing lower vapor pressure than what's predicted, that means there's less molecules getting into the gaseous phase. And so what that hints at is that there's very strong attractions between A and B. And those forces, those attractive forces, are stronger than the attractions between A and A or between B and B. So an example of this is with hydrochloric acid and water. The adhesive forces between these two compounds are very strong, stronger than the cohesive forces between like components. And then scenario 3 is the opposite situation, positive deviations. Now what could cause this? We'd be getting a vapor pressure greater than what's predicted by Raoult's law. An example here is with ethanol and water. And the way we can explain it is that A and B don't really want to mix in this case. And the forces attracting A molecules to B molecules are weaker than the forces among A molecules and among B molecules. And so that forces the molecules to want to leave the solution to get out of this kind of mixing scenario. They'd rather sort of be among molecules that are like themselves, and so that ends up just leading to evaporation because there's almost and that leads to greater amounts of evaporation. So one way to explain it is that there's stronger cohesive forces than adhesive forces here. There's a disinclination to mix, and so that allows both components to escape the solution more easily. So we will link the next couple topics to Raoult's law, but we'll stop this video here for now. Thanks.